Hey folks. Okay, I want to spend just a little bit of time talking about the code standards for this semester for our 161 labs and projects. I'm not going to spend a lot of time going through this. I will let you read them through because there is a fair bit of detail here, but I want to hit some of the highlights. Again, the idea is that these standards you do need to follow for all of the code that you turn in for your labs and for your project this semester. And they actually go beyond just the code standards themselves. There are also standards for the processes that I'm going to expect you to follow, and processes for things like documentation, some standards for the make files and things that we're going to be using. So I want to go through and give just a bit of a rundown on this. For the most part, as you're reading through the standards, I've tried to provide some of the reasoning, the rationale behind why those standards are in place. Again, I am going to get you to adhere to these pretty closely. If you think in any given circumstance you've got a good reason for not following one of those standards, then get approval from me in advance. Give me at least a couple of days ahead of whatever the deadline is for the project or for the lab. If you think you've got a good reason for doing this, get in touch with me, say, here's my reason, here's what I'm doing, and I can give you a yes or a no and say, well, no, I really do need you to stick to the standards on this one, or I might give you an exemption to say, for this particular lab, for this particular scenario, yeah, okay, you can use this other approach. But you do have to get approval from me in advance, well ahead of time. Earlier would be better, but at least 48 hours before the deadline. Let's see, some of the things that I wanted to touch on. Again, I mentioned that the standards cover more than just the raw code itself in terms of compilation and execution. Again, I'm going to run everything on our cubs and pups, and for all of them, I'm going to compile with the warnings all and warnings extra turned on. So I do want you to use those options. They're set in the make files that I provide, and I'm going to expect you to include them in any make files that you create or modify later in the course. If your program produces any warnings under this, any errors under this, you will get penalized for this. There is no warning that is too small to fix. So code that generates lots of warnings is not regarded as trustworthy. You must fix them. Ultimately, I'm going to get you to go through and generate, when you're generating warning messages or error messages inside your program, I'm going to get you to direct them to cerr, to the standard error output stream, not standard output, so not using cout, for instance, in the IOStream library. We will talk about that in the lectures as we get to more of this material. So we'll talk about the different output streams that are available fairly shortly. For the first lab, I'm not going to worry about this too much because you won't have had much of a chance to for me to talk to you about all this. But starting with lab 2, I am going to get fairly sticky about the use of cerr, the standard error output stream. Your program must run without crashes and without generating runtime errors, runtime warnings, so as opposed to the actual coded warnings that you put in your code. So essentially, if the system is throwing out any errors or warnings, that's a problem in your code, and you should be able to tell the difference between output messages that you put in the code and output messages that are coming from the system as your program's running. Again, the intention is that all work in this course be your own work. If you found code somewhere else that you want to incorporate in your solution, again, you absolutely must give proper attribution for that code. You have to make sure that you have the right to use that code, and you have to give me explicitly what code you used that came from some other source. Anything else is plagiarism, and it will be grounds potentially for academic misconduct. So you must have proper attribution of anything that comes from another source. I will expect you to know and follow good habits in terms of error checking of user input. And for the most part, we'll get into details as we work through the different labs. As we get further and further into the course, I'm expecting you to be able to recognize what appropriate levels of error checking should be. But again, we'll get into that as we get into more details of the labs and projects themselves. As far as output goes, give your messages, give your output meaning. Make sure that there's, if I ask you to output, the I don't know, area of a circle, don't just go through and spit out 47.5. Spit out the area of circle, whatever the circle is, and the number. Make sure that the output has meaning for the user. The same thing with error messages. If something goes wrong, if the user is supposed to enter a value between 1 and 25 and they enter 37, don't just spit out error or don't just spit out bad number. Give them an idea of specifically what's wrong. That number was greater than the maximum 25, or that number was less than the minimum 1, or something like that. Make sure that your output is meaningful and clear. And again, I am going to penalize programs that do not do that. As far as commenting goes, we'll be a little bit more relaxed than we were in 160. Ideally, what I want is for your code to be clear and readable. That means that the combination of identifiers that you're using and comments and layout should make the behavior extremely clear. If you're trying to decide whether your code is clear enough to read or not, whether it needs additional commenting to explain it or not, then perhaps the best way to think about it would be say, well, if a peer, let's say if a 161 student from somebody else's course was reading this code, so they didn't know the details of the assignment, they didn't know the details of which functions you were supposed to be using, that kind of thing. So if somebody else was reading this code, would it be obvious to them what you were doing? Would it be clear to them what the code is doing? So that's the kind of level that I want in terms of explaining your code, in terms of creating clear code. And if you're in doubt about something, if you're wondering whether something needs more comments, feel free to ask. Right? Go through and say, well, I've tried this, and especially in the early labs, I will try and give you feedback about where I think the more explanation or more clarity is needed. But it is something that we'll try and refine as we work our way along. Try and strike just that right balance of good, useful comments. Again, with layout, I will be a little bit more flexible. For those of you who are in my 160, I was pretty restrictive in terms of what your layout had to be. I do expect you to follow good and consistent practices with indentation to show different control blocks, different scopes. I expect you to make good use of blank lines of vertical white space to separate different portions of the code. So again, we're trying to make the code easy to read, easy to follow, and we're using the layout as one of the tools to do that. Same thing with identifier names, right? We're trying to pick identifier names that make it clear what the purpose of that function or that constant or that variable or that parameter is. Using a whole bunch of variable names like AA, II, B, C, X, I, they're not terribly intuitive, right? They don't convey meaning to the reader. You want to make sure that you're using names that reflect the specific purpose of that variable or that parameter or that constant. I will expect you to use constants and not hard-coded literal values in your code. Right? Anything where, with a few exceptions, zeros, ones, and twos, I don't mind if those appear in the code depending on the context. But for the most part, if there's a value that we're going to be using that might wind up getting used more than once, or that might wind up getting changed over time, or that simply doesn't have a clear and obvious meaning on its own, then it needs to be a constant. Global variables are something that some of you were allowed to use in 160. That is absolutely not the case here. Global variables obscure the control and data handling in a program, especially as you get into larger programs and as you get into team projects, and I am going to absolutely forbid the use of global variables in this course. Global constants are fine, global variables are not. There are circumstances where global variables are appropriate, but I will save discussion of that for another course. Let's see, file I/O is something that we'll talk about a little bit as we get more into that material itself, but I do expect programs to be responsible for explicitly closing any file that they open and for explicitly testing any file that they attempt to open. I will expect you to use reasonable top-down design, reasonable use of functions, reasonable use of methods. If you've got some chunk of code that you use over and over again, I don't expect to see that cut and paste into all sorts of different places. I do expect to see it abstracted away as a function. Go-tos are pretty much explicitly forbidden. Again, this is something where there are occasionally circumstances where they're appropriate, but we'll save the discussion of that for later courses. Break and continue. Break, well, in switch statements, you're pretty much going to have to use it, but break and continue I would like to see used sparingly, if at all. There are circumstances where they're useful, but anything that sort of breaks the normal control flow of a loop tends to obscure things, and so I would like to see that used sparingly, if at all. Array sizes will need to be, if you've got a statically declared array, then you need to specify its size using a constant or a constant expression, not a variable, not a parameter. So this kind of thing where I've got some integer value size that I'm taking as a parameter and then creating an array of that size, that is not a constant value and it's not permitted in this course. It's supported by some compilers, but it's not one that we're going to permit here. If you want to do something like this, if you have an array whose size you want to determine at runtime, then we'll use new to go, or malloc or calloc, to go through and allocate it dynamically. So that is another one that we'll watch out for. Memory allocation, anytime you do use new to allocate something, I will expect your program to explicitly have an appropriate delete of that before the program exits. Right? So every program is responsible for explicitly deallocating its own dynamically allocated memory. And I will expect that header files are in use this semester. So any constant definitions, any type definitions, structs and classes and that kind of thing, the declarations go into the header file. Profiles for all of our functions go into the header files. I'll expect header files to have appropriate guards around them to prevent multiple inclusions. So if not defs or pragmas. And again, we talk about those in the section on compilation. I'm going to expect that, again, type definitions belong in headers, prototypes belong in headers, variables do not go in headers, and function implementations do not go in headers. Every class must, again, be defined in the header, declared in the header. Every class must have a constructor and destructor when we get there. And we'll get into the details of the use of public and private as we get into classes themselves. And the other one is, I don't want folks to use namespaces globally. So in 160, we often used the sort of using namespace standard as at the beginning of our programs to just say, I want to be able to use any name from the std namespace. Well, I'm going to get you to avoid that this time around, and instead we will explicitly identify which portions of a namespace we're going to use. So if I'm going to be using string from standard namespace, I can either say using std string to indicate that I'm explicitly using that, or within the program itself, when I want to use the string type, I actually specify it using the std : string. So a bit of a change for the use of namespaces that we'll work with this semester. Makefile, there's not too much that we're going to get into here, except that in things like the make clean, I'm going to get you to avoid using wildcards as part of remove statements. Again, just because it has the risk of removing things that we didn't intend to. But we'll talk about that more as we get into writing our own make files. Documentation. The biggie that I want is for your program, produce a README that details the correct way to run your program, any known bugs in your program, any way in which your implementation differs from the specifications. So what I want to know here, or what I want this to reflect, is that if there are bugs or ways that your program differs from what's expected, I want you to document it so that you can show me that you realize that this bug is present, or you realize that you've not followed the specifications. If you do that, you will be penalized less than if you have bugs or don't follow the specifications in ways that you apparently don't even know about. So do make sure that you document any places where you've got a known bug, any places where you know that you haven't followed the specifications. And again, there will still be a penalty for not following the specifications or for having the bug, but it will be significantly less than the penalty for not even realizing that that bug is present or that you failed to follow things in the specified way. All right, the other one is that we'll be using Git for version control, as we talk about in the labs, and for submitting programs, obtaining and submitting labs and projects. One of the handy things with Git is that, again, it gives us a way to go back later and look at which changes were made to the code in each of the different commits that we create over time. That means that if I kind of logically group my changes into commits, then I can look at all of the code relevant to a specific change. So if I go through and I change the way I do input in my program and it winds up involving changes to a couple of different functions, so I change the error checking or something like that, then I put those changes into a single commit with a message that reflects the fact that this commit involves changes to the error handling for blah blah blah. So this allows me later on, when I'm reviewing my code, reviewing commits, I can see the commits have logically grouped changes to the code. And that does make maintenance later on much simpler. So this is a habit that I want you to start getting into. It's not something that I'm going to be heavy-handed about. It's just a good habit, a good practice that I want you to start working with. And so I will start including comments in your feedback for the labs about where things really should have been broken up into separate commits, where in this commit you did these things, and in this commit you did these other things, and in this other commit you did these other things. So that's something that we're going to aim for long term. All right, that is a quick run through. Again, I would like you to go through and read those specifications, the standards in detail, because you will be responsible for following all of them. But in a nutshell, that's the idea that we're looking for.